everything. Yeah.
Yeah, I have started the recording.
Okay.
Good.
So
Thank you.
yeah, can I start now? Yeah. So this is the presentation for introduction to machine learning. So basically, machine learning, it comprises of all artificial intelligence, machine learning, and the deep learning. So machine learning is a subset of artificial intelligence. And when we deep dive into deep learning, it is a subset of machine learning where we can utilize the artificial neural networks. So the definition of machine learning. So learning is any process by which a system improves its performance from an experience. So another good definition of machine learning is it is a study of algorithms that improves their performance P at some task T with experience E. So now we can see here, for example, if we are classifying an email, if it is spam or not. So that would be our task. And the data is being labeled as spam or not spam. So that will be based on our experience. And how many correctly classified are spam or not spam will be our performance. And we can improve our performance based on the experiments and the task we have. So machine learning versus the traditional modeling. So traditional modeling where we have a data and set of rules, and then we form the answers. So that is how previously we used to compute the results, like if and else statement. But now in machine learning, we use the data and the answers, which are the labels here, and we try to form set of rules, and from the rules we can learn and predict our results. So going to the next slide. um, yeah, so where we can use machine learning. So machine learning is used in every domain these days. So like from human expertise, where the human expertise doesn't exist. Then the speech recognition, where Alexa and Siri are the best examples of it. Then personalized medicines, where we can like uh, get the medicines where the patients are being correctly diagnosed with some treatment, or how it is influencing on them. And next example is genomics, where the genomic data science is also a big industry where we tend to find the patterns in the genomes of a data. So basic workflow of machine learning algorithm. So the most important part is the data collection. We need to collect our data. Then our data is needs to be pre-processed. We won't get a good data every time, so we need to process our data based on our business case. Then the machine learning models, or the training of a model, where we use n number of different data mining algorithms. Then comes the model evaluation, how good our model is. So based on the R square and other evaluation matrices, we can see where how good our model is. And then based on the uh, parameters, we can improve our model with the help of hyperparameter tuning and other stuff. So the essential machine learning algorithms. So there are many data mining algorithms such as linear regression, logistic regression, decision tree. Then the random forest is a collection of decision trees. SVM is the support vector machines. the k nearest neighbor, the dimensionality reduction, k means, which is for the clustering, and the naive Bayes. So we'll go into each of the algorithm in the next slides. So machine learning. So all the algorithms are divided into two parts. So supervised learning and the unsupervised learning. So supervised learning consists of classification and regression. So basically supervised is where we have all the labels for the data. That is, we have the answers and we predict whether it is correctly classified or not. So when we go to the in unsupervised learning, we just have the input data and we try to form interesting patterns in the data and then cluster amongst the similar items. Yeah. So this is more of a theoretical part where supervised learning, again, as I said, it requires a teacher, which means it to respond to the data. And the examples are classification and regression. So semi-supervised, where we need both the data as well as the labeled data as well as the unlabeled data. So the best example for it will be the uh, rank of a web page, where we can calculate how much time a person has spent on the website. Coming to unsupervised learning, again, it is a unlabeled data. The example is clustering, and it is mainly in the retail domain, where the market basket analysis or the recommendation systems like YouTube recommendations or the Netflix recommendations are important. So a pictorial representation of all the supervised and unsupervised learning. So the classification here, it classifies the data into the class labels, say it as 0 or 1. When it comes to regression, it is a continuous value. And this line is a best fit line for the model. In unsupervised learning, we have clustering. So these clusters are formed based on the similarity amongst the items, and the association. So associations are the a priori algorithm, which is used for market basket analysis in retail. Yeah. So regression and classification. So the difference between regression and classification is regression, again, it is a continuous value. So what will be the temperature tomorrow? So it will be a continuous scale. The meaning that the values can be a float also. So here it is 84. So 84.1, 84.6. So this is a continuous form. So this is called as regression. Next, the classification. Will it be hot or cold tomorrow? It doesn't have any relevance with the temperature as such, because we don't want any um, continuous value. So we can have a threshold of somewhere here about 60. So below 60, it will be cold, and above 60, it will be hot. So in the next slide, so now we can go deep into regression approach. Yeah. So in regression approach, we predict the value of dependent variable based on the value of at least one independent variable. So if we have one independent variable and a dependent variable, it is a case of simple linear regression. As the independent variables increase, it will be a multiple linear regression. So it describes the relationship between an independent variable, which are our features, and the continuous dependent variable y. So the basic equation of regression is yi is beta naught plus beta naught x1 or xi plus the error term. So here beta naught is the y-intercept, and beta 1, beta 2, again, it will be slope coefficients, and xi will be our independent variables or the number of features we have. Yeah, so there are four basic assumptions for regression, and all the regression models should satisfy these assumptions. So the first is linear relationship. There should be a linear relationship between the independent and dependent variable. Second, the independence. So all the residuals should be independent. There should not be a correlation between the residuals. Third, the homozydicity. The residuals should have a constant variance. And the next is normality. So the residuals of a model should be normally distributed. So in the coming slides, we can see in depth about all the assumptions. Yeah. So for the linear relationship, so in this graph, we can see that we have a linear relationship. It is a straight line between x and y. But in the second graph, it is there is no linear relationship. And in the third graph, we have a exponential increase. It is a relation, but it is not linear. So to remove the non-linearity, we can use the square root or the reciprocal of the independent of or the dependent variable to make it linear. The next assumption is independence. So in the independence, the residuals are independent. In particular, there is no correlation between the successive residuals in the time series data. So in this graph, we can see that there is no dependence on the uh, amongst the residuals. A random pattern of errors indicates independence of errors.
Rohit, when you talk about
Yeah,
Rohit, can you
yeah.
explain what is the residues?
Yeah, residuals are basically the errors. I'll get to the errors in the coming slides.
Okay.
Yeah. Okay. So the next slide is about the third assumption, that is homozydicity. So the residuals should have constant variance at every level. So residuals are the errors where we have a threshold line. And so if the residuals or the data points are equally distributed amongst the threshold, the below the threshold as well as the above the threshold, it indicates the homozydicity. So in the other two graphs, we can see that there is in this part, there is no equal distribution where these two parts are equally distributed amongst the residuals. Same goes with this graph as well. So common way to fix the heterogeneity is to transform the dependent variable. And the way to do is to take the log transformation, which will make the data normalized and linear as well. So the next assumption is normality. So the residuals or the data points here of the model should be normally distributed. So normally distributed, again, we can have to have a linear relationship. So in this graph, we can see the line, it goes through all the data points. Compared to this graph, it has an exponential increase again. So to remove this exponential increase and to make it similar to this graph, which is a linear relationship, we can apply nonlinear transformations such as log transformation or square root transformations.
So what is the QQ? What does QQ
Yeah,
plot mean?
let me
What does
go. Yeah, so QQ plot is a quantile plot. Yeah. So basically a quantile is like a quartile. right? So a quartile is 25%. So 100% is a quartile, that is a percentage. So when we take our data, it should be between 0 to 100. Or when we represent it on a box plot, it will be more relevant to see, because as you see in this graph, you can see this line from this point to this point, we can say the data is quite linear, right? But the above points are non-linear. So this is just a representation to see whether our data is normal or not. So these points may be considered as the outliers here.
Rohit, I have a question.
Yeah.
So, I mean, big picture wise, when we're talking about residuals
Right,
and normal distribution of residuals,
right,
meaning, let's say we have all this really good data
right,
that predicts the model, right?
right,
And it has a linear relationship, it has a exponential relationship, it has something more complicated,
right,
right? Right,
right,
right. So let's say 80% of the data is good data
right,
that predicts the model,
right,
right? And so we're now looking at the 20% residuals that are kind of, maybe not such good data. They're outliers, they're errors.
right,
We don't know, right?
right,
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 right. And so now we want to see, are those errors at least similar or normalized,
right,
right, to what the model would predict the errors would be,
right.
right. So that's what
Yes,
we're trying to do here,
yeah,
correct? Right,
yes,
because if they were not normally distributed, right,
right.
right, they'd say oh no, there's some we got a consistent pattern here of
Yeah.
the
Yeah,
errors.
again, it depends on the business case as well. So in medical, as example to take, as in medical case, if we see, so when we go to the data, we can see lot of features like weight are not defined. So it again goes with the EHR data as well. So where we have a data privacy, so weight cannot be uh, due to some privacy factors, we can't record the weight column. So in that case, we can just remove the data, or we can just apply random values to it to make it linear, or to have some correlation between the height and weight of a person.
Right. Well, I think we have to be careful, right? Because I think we have to define it, because if the data, if you're, let's say, doing unsupervised learning,
Yeah,
right, uh, the data is telling you that there are more variables than you've defined,
right,
right. So you can't automatically fit your machine learning algorithm, right,
right.
because you may not know all the variables, you
Yeah,
know,
exactly.
right. So I think
So
that
it
they,
again depends on the algorithm which we are going to use. So it again, we can just try multiple algorithms and then see which algorithm predicts the better results, and then we can choose a model for our best fit of data.
right, and so I guess that's kind of the limitations of machine learning, and
Yeah,
right, and so then deep learning would be, okay, looking at these other patterns and saying, wait a second, the machine learning algorithm's
yeah,
wrong,
yeah,
right? Big picture, right?
right, right.
Like with the artificial neural networks, trying to decide if there's a better model,
Yeah,
you know. Okay,
they have lot of connections and everything, so we can learn better with deep neural networks. Yeah,
thank you. No, very interesting, very helpful. Thank
yeah,
you.
yes. Yeah. So in the regression model, so we have three parts: the total sum of squares, which is equal to the regression sum of squares, and the residual sum of squares. So and the analysis of variance. So analysis of variance is, so we have n number of classes like 0 and 1. So we have two classes. So the variance of the data should be equally distributed. So again, it goes into the confidence interval and everything, but due to introduction limitations, I didn't include those parameters.
Yeah, Rohit, can you maybe explain these parameters a little bit in detail? Okay.
Yeah,
And
yes.
how to compute each of these squares? Okay.
Yeah, yes. So basically, the sum of squares, the total sum of squares, so that is yi minus y bar, the whole square. So yi is the average value of the dependent variable. So where we take the y is our dependent variable, and we take the mean of it. So yi is the observed values, so which we have in our data, and yi hat is the predicted value. So it is the model predicted value. And when we find the difference between the observed values and the predicted values, then it is known as the residuals, or the error between the values, which are the actual values and the predicted values. So regression sum. So regression sum of squares is the summation between the predicted values and the mean of the average. I mean the average of the dependent variable. And when it comes to the error or the residual sum of squares, it is the yi, that is the observed values which we have in our data, subtracted with the predicted values and taking the sum of squares over it. Yeah. So
And Ron, can I ask you one?
yes, Professor.
So
Yeah.
when you actually apply this to solve, you know, specific questions,
Yeah.
how do you? So you're gonna do you need to write the computer programs to implement this, or there's
No, Professor, there are predefined libraries which do everything for us. So when we call the libraries at the back end, all these parameters are calculated, and we can just review the performance parameters and get to know what exactly the algorithm is doing.
so you just need to call the function.
Yeah, we need to call the libraries. Yeah.
And so Rohit, is this like a linear regression, like the fundamental rules like implemented in machine learning? Because because the real experimental data can never be continuous, right? So for this,
Yeah, it
for
is a
data,
case of regression.
Yeah, so this is really like always using this linear regression, trying to
To interpret our data and get the insights about our data, we can apply regression and see how well our data is fitting to the regression when we have a continuous value.
Okay.
Yeah.
Young, I've got a question for you.
Yeah.
Young, I mean, like, if we're talking about things like, what we're talking about in nanorobotics, piezoelectric, and some of the mechanics of electrical to mechanical conversion,
Right.
is it something that really follows within this linear regression model, or is it more complicated than that?
It could be complicated than this, but this is like, I think this is like one of the fundamental. I don't know if there's any other procedure or approach. This is definitely one of the approach to relate to the non-continuous state. Right? Like if you have a function, then your input can be continuous, right? The output can be continuous. But if you are just doing like a training data, right? It can never be continuous, right? You push like say if it's a contact force, you have 1 Newton, 1.2 Newton, 1.3 Newton, right? There's no data between 1 and 1.2.
Right.
So those data, I think I'm assuming like it would be just those kind of relation will be built like use this regression.
Right. Right. Because that makes sense. Because then, because especially if you get, finite enough in your spatial resolution, your temporal resolution, right? The little interpoints that between those. And then, as Rohit is describing, if you're seeing big jumps, right?
Right.
If something is thresholded, or if it's, enzymatic,
then you may have a larger errors maybe, right?
right. And then you would say, wait a second, we're missing a variable because the data doesn't fit
Right,
the
right.
model.
So you either increase the number of variables or increase the number of training data, right?
Right.
So that can reduce the errors.
Okay.
Yeah.
Okay.
Yeah, again, as I said, this is a preliminary approach, and when we get into deep neural networks, so again, it will be an advanced version. So where we can capture all the data and get our outcomes based on our desired results. Yeah. So again, yeah. So R square, we can see the R square as it is the regression sum of squares divided by total sum of squares. And this is the evaluation metric for our regression model. So as the R square is between 0 and 1. So by higher the R square value, better is our model. So when we say that if R square is 0.98, so we can say that our data is more fitted to the model and our predictions are likely with the observed values.
Yeah, so R is larger means the error is smaller, right?
Yeah, error is basically 1 minus the value. Yeah.
Right.
Yeah. So now coming to classification approach. So classification is now in the dependent variable is 0 or 1 or true or false, yes or no. So this graph again it shows so class A and class B. So this is the classification approach.
So it's a classification for what?
Classification of the data. So again, this is a supervised algorithm where we have labels for certain data. So if we have one data entry and its label is yes, so another we have it as no. So then when we are predicting a value, so it should predict yes or no. So the prediction will be if it is equal to our observed value of yes or no respectively, it is classified as correctly. So again, the example of classifying the emails as spam or not spam. So if it is a spam, it will go into the class 1. If it is not spam, it will go to the class 0. So this is, yeah.
Yeah, so the class is here is a special term, right? In the first bullet, it's a target,
yeah,
right?
yeah. So if again we go to a medical data, so if our business case is to see whether if a patient will be admitted to the hospital or after his discharge after 30 days or no. So again, that will be a classification problem where we can see all the input parameters, what medications and how he was treated, and his readmission before 30 days or after 30 days. So before 30 days will be labeled as 0 and after 30 days will be labeled as 1. So here we don't have the exact number of days when he will be readmitted. So it will be just a threshold before and after. Yeah.
So it's just determine whether a data point is valid or not valid, right?
Yeah. Yes.
Okay.
It will fall into either of the class.
Okay. Yeah.
So I mean, so like an example, Young, that that we were using in some of our aneurysm detection or imaging AI is that you label what are the pathologies in vascular or imaging, right? So like, oh, here is a pixel of an image that's an aneurysm, and you go, this is class A, this is positive,
Yeah.
right? You know, and then you label the same the imaging that's class B that, oh, there's no aneurysm.
No, yeah, right.
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 And so, and you put in thousands and thousands of data points, right? To get it to learn what are the associations. But then I think it depends. I mean, and I'm sure Rohit knows this, but I mean, like on the size of your covariables, because just by naming a data point, it's very easy to threshold things, right? It's
Yeah.
above a certain level, below a certain level, right? But but to classify things as with collateral information, just like he uses the example of spam or not spam,
Yeah.
right? It's like, I may be interested in, cycling information, but I'm not interested in cycling information from Asia, right? So it's got to figure out the collateral variables as well.
Yeah, and again, it will go into clustering, where we can find the similarity between the data, and then it will classify or cluster the similar data points into one class. Right?
Yeah.
Yeah. Yes. So classification, again, it is of two types. So binary classification, like I said, it will be just yes or no. Or the multi-class classification, where we have multiple classes. Yeah. So like when we are um now like classifying a digit. So now we have 10 digits. So we will have 10 classes. So that will be a case of multi-class classification.
Okay, so it depends on the type of problems, right?
Yeah,
Some of
yeah,
them
yeah.
would be
Again, it
simpler,
depends
so
on
you needed two, right? Two different classes. Right?
yeah,
Okay.
yeah. So in this example, we can say that we have three classes. One is the circle, one is the hexagon, and one is the triangle. So it depends on the data which we have, how many classes we have. Yeah. So the basic data mining algorithms. So as we saw in the previous slides, the k nearest neighbor, logistic regression, support vectors, decision trees, random forest, and the artificial neural network. So we'll go through each of the data mining algorithm one by one. So k nearest neighbor.
So Rohit, can you explain like the relation between the different like can you go back to the previous the
Yeah,
summary of the
yeah.
approach techniques, right? Like so basically machine learning, like you have different techniques that you can use, right?
Yeah.
Like these are the different kind of techniques. May probably use some different principles, right?
Yeah.
To
Yes, these are the algorithms, machine learning algorithms, which will tell us how our data is well predicted according to our actual values.
okay.
So these are just algorithms, and when we apply each of them to our data, we can see the model parameters, how well it has predicted our results, and based on which algorithm has predicted our data well, we can choose that model for our further business case.
Quick question, Rohit. Is this
Yeah.
is this the entire universe of data mining techniques? Or are these the most is this the top 6 or is this the whole thing?
Yeah, these are the top 6 which are mostly used in
The top
business
6.
case, because there are many naive based and clustering algorithms and everything. Again, as I said for introduction, I thought that these are the most used, so I can go through these
Yeah, that's
first.
great. Perfect. Thank you.
Yeah, yeah.
So Rohit, so when how do you decide which one to use?
Yeah. Like when we clean our data, we just apply all the algorithms. So these algorithms which are mentioned on the slide. These are used for classification. So when we apply k nearest neighbor, we can see the accuracy of the model, the F1 score of the model, the recall of the model. So these are the evaluation metrics where we can see how good our model has performed. So based on these three parameters, and also coming to classification algorithms, the area under the curve, where we plot the ROC characteristic of the model. So how much well the area, I mean the area under the curve, better the area under the curve, better is the model. So these are the evaluation metrics where which we use to analyze all the algorithms, and then which is the best one we can choose as the best model for our data.
So when in real problem, you essentially just say you wanted to compare these different models, I mean different techniques, and see
Yeah,
which one give you the best fit, right?
yeah, yeah. We can run our data over all the models, and then based on the accuracy or the F1 score, as I mentioned, these evaluation matrices. So then we can choose the best model out of it.
I guess later on, if we have a real practical problem and question, then we can try to apply this and see how it goes.
Yeah,
As
yeah,
an example, right?
yeah, yes. Yeah. So the k nearest neighbor. So this algorithm is used for classification problems. So KNN, it is a non-parametric and lazy algorithm. So by non-parametric, we mean that there are no assumptions about the underlying data distributions. So like in regression, we said that our data needs to be linearly distributed or it should be normal. So in this case, it doesn't care about the data, how the data is distributed. And then when we say it as a lazy algorithm, because it does not need any training data point for the model generation. So again, it forms so K is the kth nearest neighbor. So in this, we can see if we have mentioned that K is equals to 3. So so these two objects are from one class and this is from the another class. So when k is equals to 3 and this unknown data point comes into picture, so this we will find with the help of Euclidean distance or the distance measure. So there are types of distance measures commonly used as Euclidean distance. Then we have Hamming distance as well as Manhattan distance and Minkowski distance. So yeah, so based on the Euclidean distance or the distance measure which is used, if we have k equals to 3 and this is a data point here, the new data point to be classified. So which class it will go into? So right now we have a majority of two classes, two triangles or the green class. So it will naturally fall into class B. And if we have if suppose we had another star here or two labels of class A and two labels of class B, and then we would have a data point to classify. So that time it will take it as randomly because it can't correctly say that it will fall into class label A or class label B. Yeah. So now to decide the k value, as k we need to specify the k value before we implement the algorithm. So uh, to find the optimal k value, there is a method called as elbow method. So it is the graph between the distortions versus the k. So distortions, basically it finds the distance and the law of inertia between the points, and this is the graph. So it forms a graph like an elbow, and where this elbow cuts down, we can choose it as the optimal value of k. So in this case, we can choose between 3 to 4. Again, it depends on how accurately the algorithm will perform with 3 and 4. Again, it's a trial and error where we can choose between 3 and 4 based on the accuracy metric. Yeah. So the next algorithm is logistic regression. So logistic regression, again, it is a supervised classification algorithm. It is known as regression, a logistic regression, and it is used for classification. So basically it uses a logit function or the sigmoidal function, which is the S shape, and this is the threshold value. In common practice, we take it as 0.5. So basically, if the probability value is above 0.5, we will classify it as in class 1, and similarly, if it is lower than 0.5, we will classify it in uh, 0th class. So this is the relation between the linear regression and logistic regression, where linear regression has a continuous data of classification, whereas logistic regression has the classes. So class labeled 0 or 1 or yes, no, like that. Yeah. So next week, the question might arise, why it is called as regression when we say that we are applying it to classification algorithm. So as you can see, this equation is same. The underlying equation is same for both regression as well as logistic regression. So the only difference is the sigmoidal function, where the sigmoidal function is 1 upon 1 plus e raised to minus y. So minus y, this will be the entire linear regression term. So this we use basically to likewise in linear regression, we have a continuous value or the probability value. So probability might range between 0 to 1. But now when we use a threshold, which is used by the sigmoidal function, then we can classify the data into class 0 or class 1. So basically we are converting the continuous variable into the discrete variable, that is 0 and 1. Yeah. So the next algorithm is support vector machines. So yeah, support vector machines is also another classification algorithm where we find a hyperplane. Again, the hyperplane is the n-dimensional space. So n is again the number of features we have. So if we have just 2 features, then our hyperplane will be mentioned as line, as we can see here in this graph. So in 2 dimensions, our hyperplane will be a line. So when we go to 3 dimensions, 4 dimensions, so visualizing our data will be difficult. So how to choose this optimal hyperplane? So again, the margin between the 2 classes, better is the hyperplane, so that if the point is somewhere here, we can classify it as into the class with blue label, and if the data point is here, we can label it with the red point.
And this has to be supervised learning, Rohit, right?
Yeah, yes.
We can't do unsupervised with this.
No. So again, unsupervised, it goes into clustering. So
Right.
these,
And so you could probably go unsupervised first, right, to come up with a hypothesis and then test it with a support vector machine to see if it, if it's
yeah,
You have-
again, so if our data has labels in it, so then we are bound to use supervised algorithms because we have the observed values or the prior data. So
Right.
when we don't have a prior data, we can go into unsupervised or clustering algorithms
Right.
where we find the underlying patterns in our data.
Okay. So yeah, because you need ground truth.
Yeah,
Or
exactly.
right. Got it. Thank
So
you.
what is like the vector machine here? Okay.
Yeah. So in next slide. So vectors. So these points which are on the margin. So this line will be our hyperplane, right? So in the margins between the hyperplane are the two bounds of the margin. So support vectors are these points. So 1, 2, and for this class, this will be 1 and 2, and for this class, these three will be the support vectors.
The
Yeah.
vector, the support vectors, the origin of the vector is in the bottom.
Sorry.
For the vector, I'm thinking about those mathematical vectors.
Yeah, it's a real mathematical vector. Yeah.
Real vector. So where is the origin of that?
How was the vector defined?
How do you, yeah, how do
Okay, so these support vectors are the data points. So when we increase the margin, so the data points on the margin are known
oh,
as are known as support vectors.
I
So
see. So
data points, yeah, when we represent our data into matrix form, so again it will go into vectors. So from that understanding, we say it as support vectors.
so the vector basically are those
Data point.
data points in the two different classes where you
Yeah,
And Rohit, you're describing for, for the purposes of discussion,
Yeah.
a two-dimensional simple version of this, correct?
yeah, yes.
Right, right, because you can imagine multivariable, three-dimension, Fourier transforms, you know what I mean?
Yes.
Right,
Yeah.
right? So you could upscale this, or
Yeah.
that's being done, right? Because
Yes, yes.
most things are not this simple, right?
Yeah, exactly. So we can have n number of features, right? So right now, when we have two features, so it's better to visualize and get the intuition behind the algorithm. Yeah. So next is decision trees. So decision tree again, it works on the approach where it is drawn upside down. So this is the root node, and the last node is a leaf node. So we can use decision trees for regression as well as classification algorithms. And this is the condition is sex male. So this is a condition. And based on this condition, yes or no, the further tree will be split down. Yeah. So what's going on the background? So growing a tree, deciding on which features to choose and what condition we should use for the splitting. As a tree generally grows arbitrarily, we will need to trim it down, because if we have n number of features, it will go long, and it will be overfitting to the model, or the tree will grow long enough. So if say we have three features, then we will have just three splits, and and then we calculate our accuracy of the model. So this is a recursive in nature. So because recursive as in if our first condition is met, again it will branch into yes or no, or how many conditions, or whichever conditions it has. So there is a split based on the condition which we apply. Yeah. So where to stop and how to trim the decision tree. So if we have n number of features, so again our tree will be complex and it will lead to overfitting. So the one way to do is to set a minimum number of training inputs to use to each leaf. By this I mean the number of inputs or the features. We can limit our features to our data. So like if we have hundreds of features, and when we see a feature importance about each feature, we can take top 20 or top 30, which will trim our decision tree. So least important features which we can just decline them, or we can remove from our modeling. Yeah. And the next way to do is by there is one parameter called as maximum depth of the tree. So by maximum depth we mean that how many times it can split. So if we take 3, so it will split into 3 times. It won't split more. Yeah. So again, it refers to the length of the longest path from the root to the leaf. So if we specify it as 3, it will go till so the third node will be the leaf node. It won't split after that. So the splitting, or I mean where to stop. So this process is known as pruning of a decision tree. That is, it involves the removing of the branches that makes use of features having low importance. Again, so when we look at the feature importance, so as I said in the previous example, that if we have 100 features and we wish to take only top 20, so we can just remove all the remaining 80 features. So yeah, so there are two types of decision trees basically, the Gini index and the entropy. So there are models where decision tree 4.5 is the Gini index, which utilizes just the probabilities, the sum of square of the probabilities, and the later version which uses the information gain and the entropy with the help of log function. Yeah. So after all the data mining algorithms, we come to artificial neural networks, which mimics the human brain almost. We can't say it as completely it mimics, but yeah, it tries to mimic. So artificial neural networks, we can use it for regression as well as classification. Again, there are types where if our data is images or text or speech, then we can go into convolution neural networks or recurrent neural networks. So basic component of artificial neural networks is the input. So the input data which we get, and the weights are the importance of the data. So how important that input is. And next is the transfer function. So transfer function is basically the summation. So when we multiply the input and the weights, so the summation of it is calculated in the transfer function, and then we give this to an activation function. So there are different types of activation functions as well. Based on our business case, we will use them. Yeah. So the relevance between the biological neuron and the artificial neuron, the same as how the information transfers from dendrites to axons. Similarly, the information in artificial neural it goes through. So all the information inputs are x1, and the weights assigned to them are multiplied with the inputs, and in the transfer function we get the summation of it, and then we apply it to activation function, and then we have the output. Yeah. So the artificial neural network, it consists of forward propagation and the backward propagation. So in forward propagation, we just find the values like the input layer and the weight. So this process takes place for each layer: the first hidden layer, the second hidden layer, and the output layer. So when after in the output layer, we get some predicted value. Then we compare that with the actual value. And to minimize the error between the actual value and the predicted value, we go for a back propagation step where we backtrack from the output layer to the input layer, and we try to update the weights of the connections. So when we update the weights of a connection, again, it goes through a forward pass, and it tries to minimize the error between the actual value and the predicted value. So this is the basic working of artificial neural network. So like the activations functions which we use. So one is the logistic or the sigmoidal function. So when we have a data to classify with the help of artificial neural network, we will use sigmoidal function. Then we have a hyperbolic tangent, which is similar to sigmoidal function, but it varies from -1 to +1, whereas the sigmoid function, it has a range between 0 to 1. So the next is rectified linear unit. So rectified linear unit, it just takes the maximum between 0 or the data value. So it suffers with exploding gradient problem or the vanishing gradient problem. So by this we mean that when we in this graph, if we can see, it tends to 1 after certain value. So that will be a vanishing gradient, because after 1 it can't go to a certain value above 1. And similarly, exploding gradient with a negative curve below the line. So rectified linear unit, it prevents this problem, which is occurred in sigmoidal and tan H activation function. And again, the next form of the advanced version of rectified linear unit is the leaky ReLU, where it doesn't go to the 0th point, whereas it multiplies the input with 0.1, or we can specify this value so that it doesn't have the problem of vanishing gradient or the exploding gradient. Yeah. So that's it for today. Yeah.
Okay.
Very
so
nice. That's very nice.
Thank Dr. Rohi.
Thank you so much.
I thought that was fantastic. I learned a
Yeah.
lot. Thank you.
So Rohit said like he want to give us first this week. He want to give us some like a fundamental concepts,
Yeah.
ideas about this, and then he's going to prepare some tutorials like a simple user sample problems to show
Yeah,
us
code snippets as well as the TensorFlow, and in
TensorFlow.
next lecture we'll go through the deep learning approaches.
Yeah.
Yeah.
That will be great. Thank you so much. So, maybe you can send us the the recording or the slides. I think
Yes.
that would be very
Yeah,
helpful.
Yang,
Yeah,
can
the
you,
recording.
I think
Yes.
it's, Dara, can you send the link of the
Yeah, I will share the
Sure, sure.
presentation as well.
Yeah,
Yeah.
share the presentation as well.
I
Yeah,
wanted to
sure.
give you positive feedback on the presentation. I thought your presentation skills were excellent and you did a really good job conveying
Thank
some
you so much.
very
Yeah.
complicated, you know,
Yeah,
you
and to
know,
cover
challenging
each an
topics.
algorithm, it's tough to explain in such short time because there is a lot of math behind it and everything. So I
Right.
tried to cover as much as I could. Yeah.
Yeah, it's
Yeah.
a very good job, yeah.
Very nice job. I think this is a presentation that's good for every level of background.
Yes.
It's a
Right.
great introduction. Thank you.
Thank you so much.
Yeah, so I was just talk with Rohit. He said maybe next Monday. Is next Monday okay with you, Rohit?
Yes.
Monday is fine. I think 4:30 is. Are we still gonna do 4:30 or?
Yeah, we can still do 4:30 next Monday.
So yeah, I think that should be okay. Eric, is 4:30 okay? So Eric is.
I think I mean, is 4:30 okay for everybody? I mean, as at least for the next month or two?
Yeah, because our regular group meeting is like a bi-weekly, but because like this is the beginning of, we already started the summer, so and I think like the know how to use this machine learning approach is very important. So we can add one lecture next Monday at 4:30.
Okay,
Yes.
that sounds great to me.
Yeah, so he-
I'd love to learn more.
Yeah, so
That's great.
we'll introduce like maybe use a sample project and show us.
Yeah,
how
and
to-
I will share the references as well with all the
Yeah.
team members. Yeah.
Okay,
So prior to the meeting, everyone can go through that.
yeah, that would be great. That would be great. Yeah.
Oh, by
Thank
the
you so
way,
much.
Rohit, can you also share us your PowerPoint or the presentation so we can
Yes, yes.
actually
Yes,
take
yeah.
a look on it?
Yes, sure.
Thank you very much.
Thank you.
Okay, so yeah, Rohit, so because I have your presentation, so I can email it to Yang when he send out the Zoom like the recording, the link for the recording, right? You can send it to everybody.
Okay.
Okay, any other questions?
Yeah, I think it's a great job. It's not an easy concept. So, yeah,
Right,
did very
yeah,
well.
so. Okay, so it's already 5:30, like if no other question, shall we just stop here or any?
Very nice to meet you guys.
Yeah,
everyone.
Nice to
very
meet
nice to meet you.
Very nice to meet you.
Yeah.
Thank
Okay,
you.
now I will stop the recording.
Yeah, you
Yes.
can stop the recording.